My name is Shubham Rastogi. I'm a compiler engineer at Apple working on all things debug info. And today I want to give a talk about fine-grained compilation caching using llvm-cas. I want to give some quick background to this talk. This talk is about compilation caching using content addressable storage, or CAS. And it's a follow-up from some previous talks that me and my colleagues have given at llvm Dev meeting last year and the year before. Specifically, this is a direct follow-up to the talk that was given last year about representing debug info in llvm-cas. So let's quickly go over the agenda for this talk. We're first going to do a quick content addressable storage recap. Then we are going to discuss the improvements to the debug information section representation in fine-grained object storage. Then we are going to discuss the improvements to replay speed. And finally, I'm going to talk about the object storage, fine-grained object storage for support for Swift. So without further ado, I would like to introduce MCCAS. So what we're trying to do with the CAS is to create a build cache, which is comparable to ccache. We want to split object files into CAS objects for fine-grained storage. And we call this paradigm MCCAS colloquially. The reason we are comparing to ccache is because ccache is a very easily understood tool that is ubiquitous, and so it's a very good comparison metric for us in the work that we have done. So if we want to compare ccache with MCCAS, there are some differences. So ccache's granularity is at the object file level. MCCAS's granularity is much smaller. It's below function level. And because ccache's granularity is at the object file level, there's a higher rate of growth over incremental builds, because even for a small change in an object file, you have to store the whole object file again. With MCCAS, that is not the case because we only store what we've changed. So the incremental growth rate is much smaller. And that's something that we intentionally designed this with in mind. So let's do a quick CAS object store refresher to understand how CAS works. So CAS object's address is the hash of the contents. There's a one-to-one mapping between the data that is stored in a CAS object and its address. And this is immutable. Therefore, if the data changes, the address changes as well. However, if you try to store redundant data in a CAS, instead of storing it again, you get a reference to that data. And this is what we call deduplication. And this is what we are after. This is how we are trying to reduce the size of incremental builds, essentially. So how does data get represented in a CAS? Content in a CAS is a DAG of, or directed acyclic graph of CAS objects. And each CAS object has some data and a list of references to other CAS objects as well. So I just want to talk about where we left off last year in last year's talk. And we had something that looked like this. So what does this graph represent? So because we have a build cache, we wanted to simulate an LLVM engineer's build workflow. So to do that, the way an LLVM engineer works is you come in the morning, you get the top of tree, you build, and then you work, right? So to simulate that, we took one commit per day. And so we took 10 commits over 10 days. So we have a 10-day build of Clang. And in blue, we have a CAS where we created one CAS object per object file. And in green, we have MCCAS where we split up the object file into smaller pieces and stored it in a CAS. And we can see that when you do this course, and both the builds are in debug mode, so O0, and with debug information as well, so with -E. And so you can see that when we don't do these fine-grained optimizations, the size of the CAS balloons to about 65 gigabytes after 10 builds. And not only that, the rate of growth is also very high. It's 708%, versus in MCCAS, the size is a lot smaller. It's about 17.5 gigabytes. And the rate of growth, which is the main thing that we're after, is also much smaller at about 400%, right? So what happens if we overlay the ccache number? So because we want to compare to ccache. So as you can see, we have ccache in red. What's interesting is that the size of ccache after 10 builds is smaller than the MCCAS size, right? But one thing to note is that the growth rate of ccache is larger. It's about 730% actually, because it's doing it's going to store a whole object file again, even if something small changed, right? So we believe that if you took this further and did like another 10, 20, 30-day build or something, that at some point there would be a crossover and MCCAS would actually end up smaller. But we also believe we can do better, and so that's what we're going to discuss in the rest of the talk. So yeah, with that in mind, I would like to talk about the improvements that we made since last year. So if we look at the size of the CAS at 17.5 gigabytes, we can see that the debug info section accounted for about 9.9 gigabytes out of those 17.5 gigabytes. So over 50% of the size of the CAS was purely represented by the debug info section. So if we can do something to reduce the size of the debug info section representation in a CAS, we can probably get some major size reductions overall. So to understand how the debug info section works, let's try to actually see what goes in the debug info section. So over here we have a simple CPP file with two functions, func and func2. And so when we compile it down with Clang, with optimizations turned off and with debug info enabled, and then we use DWARF dump to dump the debug info section of the object file, and we filter for func on the left and func2 on the right, we can see something like this. So this is the debug info representation for the functions. So debug information is represented as debug information entries or dies. And so in purple, we have a die that represents the function. So func on the left and func2 on the right. Some data in a die does not deduplicate. And to make sure that that does not reduce our deduplication rate, we hoist that data out and store it in a separate CAS block that we, for our purpose, will be calling distinct data here. Dies can also have children. So over here, if I pass the -c flag to DWARF dump, it will show me that the subprogram die that represents the function for both func and func2 has a die that represents a child die, which represents the parameter that the function takes. I also want to just mention the debug abbreviation section. This section contains, can be thought of as like the type of a die. If we try to look at the DWARF representation of the debug abbreviation section for either func or func2, this is what we see on the right. So what that tells us is that multiple dies can be represented by one abbreviation. So abbreviations can be shared amongst dies. So when we put it all together, we get something like this. So this is how we represent debug info in the CAS. So at the top in green, we have a CAS object that represents the debug info section. Then we have a block that represents the distinct data, which, as I mentioned, is all the data that does not deduplicate. Then we have a CAS block for the abbreviations. And then we have individual CAS blocks for dies. We're not creating one CAS object per die, but essentially we have some heuristics that we use to determine whether a child die should be split off from its parent. And if it should be, then we create a new CAS object and attach it to its parent. So once again, this is what we had last year, and it was pretty large. So we made two main improvements to this representation to reduce the size in the CAS. And so one of them was flattening the section layout. And the second one was reducing the size of the distinct data CAS object block using compression. So to get into that further, I would once again want to remind everyone that a CAS object's address is the hash of its contents. And a CAS object's contents contains not only the data, but a list of references to other CAS objects. So if any of those things change, the CAS reference changes. Also, CAS objects are always ordered. So what we were seeing essentially is that for an incremental build, if a small child die had like even one byte that changed across a build, its reference would change because it would change. And so its reference would change. Now the problem is that its parent contains a list of references to it, right, and other children that it has. So if even one of that reference changes, then the parent changes. So now its reference changes. So its parent changes, and its reference changes. So we kind of have this cascading effect where even a small change in a small die would lead to a lot of deduplication being lost, and that's something that we want to mitigate. So to change that, we went with a representation that looks something like this. So in this scenario, what we have is that we have flattened the structure, so no child is attached to its parent. And so if a child does change, its reference changes, but none of its parents change, right? And so that way we improve the overall deduplication rate that we get over incremental builds. The second thing we did is we use compression. So once again, if we look at the size of the CAS at about 17.5 gigabytes, the size of the debug info was about 9.9 gigabytes. But unfortunately, the distinct data is 9 gigabytes, right? So the distinct data is like the CAS object block that stores data that does not deduplicate. And that accounts for about 90% of the overall debug info representation. So very, very large part. And it's this huge blob of data that just has to be stored every time you do a new build. So if you take 9 gigabytes and we have one distinct data CAS object per object file, so there's about 14,000 CAS object blocks in over those 10 builds. We have 630 kilobytes per distinct data block. So that makes it a very good candidate for just simple compression. And so that's what we employed here to also reduce the size of the debug info representation. And so when you put it all together, we get something like this. So this is just like the initial graph that I'd shown, but zoomed in to just look at the debug info section. So as I mentioned before, the debug info section representation after 10 builds was about 9.9 gigabytes pre these optimizations that we made. And after the optimizations, we see that the size has gone down to a much better, like about almost 5 gigabytes, right? So it's gotten much smaller after we made these changes. When we zoom out to look at the whole size of the CAS, we can see that before these optimizations, the size was 17.5 gigabytes, and now it's gone down to about 12.5, right? 12.6. And now when we overlay ccache on top of that, we can see that after the third build, there's a crossover, and MCCAS is strictly smaller than ccache. And after this 10 builds, ccache is about 15.5 gigabytes, and MCCAS is like 12.6. To take this a little further, I also wanted to do a 30-day build instead of just a 10-day build, just to see like if this pattern holds true. Maybe we have some false positives, right? And so you can see once again, if we do a 30-day build, ccache size balloons to about 42 gigabytes, while MCCAS is 32.5. And we can see that the rate of growth is smaller. MCCAS is 1,000% versus ccache is about 2,100%, 2,200% almost. So we can see that like our initial hypothesis is correct, and the incremental growth rate is smaller, right? Another thing I wanted to do was, instead of doing like a 10-day or 30-day build, I wanted to do 200 successive incremental builds and see what that looks like. So once again, we can see that initially MCCAS is larger than its ccache counterpart, but over those 200 successive commits, over time, the MCCAS growth rate is smaller, and so overall, after those 200 builds, MCCAS ends up being much smaller. I know there are some large spikes in the graph here, but I think some of those incremental comments just changed a lot of stuff, and so a lot of object files were rebuilt, right? So we can't do anything about that. But essentially, this is what it looks like even if you do a bunch of incremental builds. So now that we have talked about that, I quickly wanted to also talk about DWARF 5 support in MCCAS. Because Darwin does support DWARF 5 starting like now, we also wanted MCCAS to support DWARF 5 as well. When we map out the size of an MCCAS with DWARF 5 versus DWARF 4, we see a very peculiar result where the DWARF 5 size is actually larger than the DWARF 4 size, which is counterintuitive because DWARF 5 is supposed to be a more efficient method of debug info storage. However, the debug info section of DWARF 5 is actually smaller than its DWARF 4 counterpart. So something really weird is happening. So if we look at the numbers, we can see that the DWARF 5 CAS is about 7% larger than its DWARF 4 counterpart. And after some investigation, we realized that the reason is because there's a new section in DWARF 5 called the debug string offset section. Unfortunately, this is also data that this does not deduplicate. It's just a blob of data that we have to store. So once again, it's a great candidate for a zlib compression. So when we apply compression to that, we can see that we essentially match the DWARF 4 size. So post-compression, DWARF 5 size is essentially identical to the DWARF 4 size that we used to have. We don't beat DWARF 4, unfortunately. But the reason in this graph you can't see the DWARF 4 graph is because it's literally hidden by the green DWARF 5 post-compression graph. So we match it. So that's the best we can do at this point. So now I want to talk a little bit about improvements to the replay speed in MCCAS. So replay in this context refers to rebuilding a previously cached build. So maybe you switch branches and then you switch back. And you have to, when you build, you rebuild everything, but the build is cached. So you would expect the build to be a lot faster. And for we call this just replay colloquially. So when we look at the replay speed of MCCAS before we did any work to optimize it versus ccache, we can see that they're basically neck and neck. They're identical, more or less. But once again, we think we can do better. There are two main issues that we noticed with replay speed. So one was we were materializing the same abbreviations multiple times. And the second is that the ULEB decoder we were using was not optimal. As mentioned before, the debug abbreviations describe the dies in the debug info section. And multiple dies can be described by one abbreviation. So it is always true that the number of abbreviations is strictly less than or equal to the number of dies. The problem that we were having is that every time we wanted to materialize a die, we were also materializing the abbreviation that went along with it. And so that's just expensive because it requires a lot of ULEB decoding. And the simple solution there was to just materialize all the abbreviations once, memorize them, and that just reduced the materialization time significantly. The other thing that we did is we were using a ULEB decoder that was unoptimal. And so when you do any materialization, it requires a lot of ULEB decoding. And we were using the binary stream reader class in LVM. And this was not optimal because it does not guarantee that a stream is contiguous. But all the CAS objects we're reading from is a contiguous stream. So that was just causing some performance overhead. In fact, this is the main bottleneck that we saw when it came to materialization time. So the quick solution there was to just replace the binary stream reader class with another class called data extractor, which only worked on contiguous streams. And so when we do that and we graph out the replay time, we can see that after these optimizations, the MCCAS replay time is now strictly faster than what it was before. And when we overlay ccache on top of that, we can see that MCCAS is now strictly faster at replaying a cache build from ccache. The difference is not large. As you can see, it's about, I believe, 8%, but it does exist. So now I quickly want to just mention MCCAS support for Swift. So Swift compiler can also create an MCCAS. Currently, we've tested only with a small open source project called Alamo Fire, and it seems to work fine. But we do require further testing to make sure that it works correctly before we can, give it the green thumbs up. So with that, I just want to conclude and say that I think MCCAS demonstrates a real-world use case of having CAS library in LVM. We believe that CAS library in LVM can lead to a lot of advantages over just using a solution like ccache. In fact, we can also cache Clang modules. And my colleague Ben had given a talk about caching Clang modules using a content-less storage last year that I've linked here as well. For future work, we want to test and benchmark MCCAS for Swift, make sure it works correctly, and make any optimizations that might need to be made for Swift specifically. We also want to implement more CAS-specific optimizations for other DWARF sections, such as the debug log section, the debug ranges section, and so on. If you are interested in contributing, we have an initial patch up with the llvm-cas implementation on GitHub. The link to that PR is here. So please get involved. Please leave your comments, suggestions, so that we can upstream this work into llvm.org. That's something that we're looking forward to seeing more community feedback on this work. And with that, I would like to end the presentation and ask anyone if they have any questions, comments, or suggestions.
Thank you. So it's not upstream yet. We cannot just use it now in Clang.
No, it's part of the Apple fork of LVM, like open source Apple fork of LVM project, but it's not in main LVM, yeah.
And when it will be upstream, it will be decentralized. You can have a server And so you can have a cache in a server, so multiple people can use it.
Like, I mean, the way, like, the way I've presented it right now, this is just for local caching. But yeah, like, so that's not something, as far as I understand it, that's not something that we're planning upstream right now or anything, but the way that's presented right now is just for local caching, not anything with like server remote caching stuff, but yeah.
And does it work with LTO?
Does it work? I mean, this is trying to, I think if you do an LTO build, it will just not create a CAS. I tried with LTO. I generally don't believe, because as far as I understand, like LTO does not emit like regular object files, right? So like, yeah, so I don't think so. Like, I think just LTO will just skip that completely, as far as I understand. But yeah, I'll be honest, I tried LTO once just to see what would happen, and the only thing I was looking for is like nothing breaks and nothing broke. So I was like, okay. But yeah.
Okay, thank you.
You can use this one.
Thank you. Did you break out, just thinking about the zlib compression that you added, did you break out whether or not that paid for itself when it came to the replay speed? I just wonder whether or not the space saved then led to like a slowdown somewhere else that was significant.
Yeah, so we didn't notice any slowdown, like nothing too large that, you know, even showed up in the data or whatever. So we think it was definitely worth it. And I did not use any specific compression ratio. Like, I just used the default compression ratio. So we could like try to, you know, increase that compression ratio and see if we get any better size improvements, but we were happy with what we got. So didn't do anything about that.
And I think the use cases you were exploring was compiling a different LLVM project build day by day, so moving forwards one day each time. Are there any benefits to be had from incremental compilations where you just are making small changes and going forwards? Is it not designed for that kind of use case? It's more trying to go further back in time?
So one of the slides I did present, and this one, I'm sorry, maybe I didn't make it super clear, but this slide specifically is 200 incremental commits. So instead of doing one, this is 200 incremental commits, like one after the other. So again, there is a benefit, but the benefit is realized over larger periods, because you know, there's only so much code that changes. But as I mentioned before, like, there are some large spikes, and I think that's because some incremental commit just changed something very fundamental and a lot of object files changed. But the point is the growth rate goes down, right? So because like if you ccache, if you just made a small change in like one function, you'd store this object file again. Or if it was something like, I don't know, small vector, you'd store all the object files again, but like not with MCCAS, right? Like that would not happen. So yeah.
Very good. Thank you.
Thank you.
Hi. Do you know if anyone has taken your work and tried to apply it to C and C++? Clang, for example?
I'm not sure what you mean by try to apply it to Clang.
So,
like this is,
oh, sorry, I mean, not in the Swift context, but in producing
so
object files.
All of these graphs that I've shown are compiling Clang with itself, but using a CAS. So this is all C++ code that, like, all of these build results are C and C++ code.
Okay.
Yeah. Like Swift is not tested that much yet. Like Swift is like later. Everything is C and C++ so far.
I see. Okay, thank you.
Just one quick question. Maybe you said that in the miss. What is it that you're building as you are building these graphs? Like 13 seconds build. What was that?
So the test case that we're using is just building LLVM itself.
Okay.
So we're building LLVM with LLVM, but and because it's like a big test case, right? So it's just like, yeah.
Sorry if I missed that.
Yeah.
But, okay, so this is the end of the questions. We're going to have 5 minutes, and then we're going to start the short talks.